Hi, my name is Will, and today I'll be presenting this work, Adaptive Sampling Strategies to Construct Equitable Training Datasets. This is joint work with Bobbie, Sam, Miranda, Stevie, and Sharad. The goal of polygenic risk scores is to predict risk of disease based on genetic variants that are present in one's DNA. And you can imagine this could be a powerful public health tool if it worked properly, right? Because you could focus interventions on people of high risk. One obstacle, however, in deploying these models in the real world is that they often perform much worse in populations of African ancestry versus those of European ancestry. And a lot of this is thought to be due to lack of representation in the training data, right? So a recent study found that 78% of individuals in the training data for polygenic risk scores are of European descent versus only 2% of African descent, which is a huge gap. And further, this problem isn't contained only to polygenic risk scores, but in fact, there are analogous examples of lack of representation in a wide variety of domains and also across a wide variety of subgroups. And so this has led to calls within the computer science and machine learning community to diversify datasets. That's kind of where the starting point of this project was. We wanted to sort of discuss what a fair training dataset might actually look like. So, okay, I think when most people think of fair training datasets, they think of some popular heuristic strategies for sampling, including something like equal or representative sampling. However, what we find is that these strategies can have unintended consequences. And so, for example, by default, representative sampling oversamples from majority groups. That's kind of what the definition of representative is, which we think is kind of a funny strategy to kind of encode as like a default fair way of sampling. And so, okay, given this, what do we actually propose? The method we consider in this paper is something we call adaptive sampling, and it's a two-step process where first we model what we call the learning curve, the mapping from dataset composition to group level model performances, and second, we specify, the model builder specifies their preferences over resulting group level model performances into a single utility function. And from then on, what we do is we optimize over all possible data set compositions to maximize the model builder's utility. And you can do this either globally using tools from something like convex optimization if you have the appropriate geometries, or something like Thompson sampling if you're in an online sampling setting. What we find is that this approach allows for model builders to efficiently construct models that take into account trade-offs in model performances between different groups and avoid some of the pitfalls of popular heuristic strategies. And further, that by specifying preferences into a utility function, the model builder can efficiently intervene to make models more inclusive for groups that have been traditionally underserved by models in the domain.